So I like to think of it as a phenomenon of AGN emission being dominated by a synchrotron component, highly polarized, highly variable at all wavelengths, high polarization variability. So the old school BLACs met all these criteria. But then there were also quasars, namely optical things, stellar optical things with broad emission lines in their optical spectra, which also complied with all these. And so the whole lot were collectively known then as blazars. So I put these things to be suggestive, and this is the optical spectrum I was talking about, BLAC spectra with no emission lines completely dominated by the synchrotron emission, and these with a significant synchrotron component, but yet broad emission lines. This picture has been seen many times in this meeting. I just wanted to point out or remind especially the new entrants into the field that there is a subtext here which says that there's an underlying SED like this below this, and we see it this way because of the beaming, although in a given case we don't know the details, such as are there emission lines or not, as has been mentioned before. So I thought I'll show this straw person picture, which I showed in my first introductory talk to this meeting. So the Faranoff-Riley luminosity divide, and that picture said that the AGNs with FR1 structure on hundreds of kiloparsec scales are the parent population of the BLAC objects, and the AGNs with FR2 morphology at the hundreds of kiloparsec scales are the parents of the quasars with beamed jets, relativistically bulk relativistic jets. The thing to remember is this identification involves only relativistic beaming, and this identification involves relativistic beaming and obscuration by gas and dust when you go from here to here, and just relativistic beaming when you go from here to there. So the straw person, much water has flowed under the bridge after I showed that straw person picture, a lot of muddy water. I won't add to that except to list a couple of things. For example, the FR1 quasar by Catherine Blundell, who's here, and Rawlings in 2001, and followed by the paper called Prevalence of FR1 Quasars, Haywood in 2007. Preeti's work with her collaborators, which showed that the Mojave blazars had 23% BLACs have FR intermediate luminosities and 60% having hot spots. On the other hand, some old work with Preeti and I did, part of her PhD thesis, where we put BLACs and FR1s on the same plot and quasars and FR2s on the same plot with the radio core dominance on the x-axis. I won't go into this in detail, but shall we just say that we got suggestively consistent results with the old school straw person scheme. So the straw person scheme is nevertheless useful to me just in terms of trying to remember the complicated phenomenology that's going on. A tip that I learned from actually Richard Pocus a long time ago, who was mentioned earlier in this meeting. So we examined the Blazar divide using data from the Fermi telescope. The 3 LAC, the third Fermi LAT catalog, in particular the 3 LAC, that is the AGN's list from the third catalog, which has 1,444 AGN. They're classified in the Fermi papers into quasars and BLACs, depending on whether or not they have emission lines, and putting together this with the Mojave data. So we don't pick all the AGNs in the third catalog. We only pick those which have, we rather deselect those with low statistical significance. This is just to quickly show you that, so this is a matrix plot of flux density versus flux, flux versus flux in the different Fermi bands. And they should correlate, of course. And you can see these pink points and the purple points, which clearly show problematic behavior. So those are the ones we deselect. This showing the same thing in the luminosity plane. The pink points and the purple points showing problematic behavior. So we select only those with reasonable statistical significance. That leaves 813 AGNs, 571 with redshifts, of which 250 are quasars and 254 are BL-arc objects. So taking data from the Mojave project, where they measure the proper motion speeds of the beamed components. Here is a plot of the Fermi gamma ray luminosity across the whole band versus the maximum beta apparent that is measured by the Mojave project over their time baseline for a particular source. So the time baselines, of course, differ for different objects. And you get the not surprising correlation of the maximum apparent beta with the gamma ray luminosity. But looking at that plot a bit more carefully and separating out the quasars and the BL-arcs, I will consistently use blue for BL-arcs and red for quasars. One can see that the most of the trend is due to the systematic differences between the blue points and the red points, in other words, the BL-arcs and the quasars, which is shown here. So this is the distribution of the luminosity of the BL-arcs and quasars, the distribution of the gamma ray luminosities of the BL-arcs and quasars. This is a box and whisker plot. Just to explain that very quickly, this line is the median. The notch gives you the 95% confidence in the median. This is the interquartile range, and these are the outliers. So this luminosity difference is not only due to redshift. So even in a redshift matched range, there's this difference in luminosity. And the maximum beta values also show a systematic difference between the BL-arcs and the quasars. In fact, the minimum beta apparent, which is measured by Mojave, also show a systematic difference. Similarly, the variability index, sorry, that's a repeat, and the variability index is also different between the two subclasses. So Ghisellini and collaborators published this paper in 2009 with the earlier Fermi data, where they plotted the photon index versus the gamma ray luminosity, and the blue are BL-arcs and the reds are quasars. And they of course found that the BL-arcs have harder spectra. This has been confirmed many, many times, which they interpreted as being due to the BL-arc jets emerging in a photon-starved environment. But then the other thing they said was from this plot that the Blazar divide appeared to be more of a continuity rather than a dichotomy. With the 3-lag data that we looked at, we see the same trend again, but if we separately look at the BL-arcs and the quasars, the BL-arcs show almost no trend, whereas the quasars tend to show an opposite trend to what the whole lot shows, which suggests, on the contrary, that it might actually be a dichotomy. So to get quantitative with all this, one way to get quantitative is to look for a robust parameter for the inclination of the jet to the line of sight. And it is customary in the literature to do this by the so-called radio core dominance parameter, which is the ratio of the nuclear radio flux density to the extended flux density or luminosity, whichever you like. The idea being that the nuclear luminosity is relativistically beamed, so when and the extended luminosity is not beamed. So if you take the ratio, when the object is close to the line of sight, the luminosity is boosted, and therefore that ratio gives you a statistical measure of angle of inclination to the line of sight. But in the case of the Blazar class, they all have, of course, very high core dominance, and within them, it's hard to use that as a measure because, for example, these are images from Preeti's paper of the Mojave Blazars, VLA A array. So the point is that to measure the core luminosity, you need a high resolution aperture synthesis measurement, and such an aperture synthesis measurement by its very nature will miss the extended flux density. Therefore you need simultaneous single dish measurements in order to get a robust parameter, which are very rare. So I'll skip these slides. So instead, we looked at the ratio of the optical core luminosity to the host galaxy optical luminosity in these things. For example, this is an example here taken with the Nordic telescope on the Canary Islands, where the seeing is very good, and so they can make the separation between the point source and the extended host galaxy. So we use those data combined with similar Hubble Space Telescope data, and we find that the gamma ray luminosity indeed correlates with this nuclear to host galaxy ratio within the BL-lac sample. Now, this is only the BL-lacs. So I will go to my conclusions. So the data are consistent with BL-lac jets being launched in a photon-starved environment. The maximum apparent jet speeds, the variability indices are higher for quasars systematically. Dependence of the photon index on gamma ray luminosity is different for quasars and BL-lacs, which is consistent with the Blazar divide being a dichotomy. Exploring the Blazar divide quantitatively requires a robust orientation indicator, which the radio core dominance cannot provide, and therefore optical nuclear to host galaxy ratio could provide a better proxy. Thank you.
Thank you very much. Questions? Up there? Oh, maybe you can try to shout.
High-powered, high synchrotron peaked blazars. So
yeah, so that is something we want to look into. For that, this sort of quantitative handle on the orientation can play a role. I just showed the results for the BL-lac object. We have to do the same thing for the quasars and then look at these trends that you're talking about.
okay, thank you.
Question here?
Prajval, so the systematic difference that you showed between the BL-lac and the quasars, but there is a systematic difference in their redshift distribution as well.
Yeah, so I showed that as well, that when you restrict them to a range, yeah, they still show.
Okay, okay,
yeah.
thank you.
Okay, one comment about the first statement that the data are consistent with BL-lac jets being launched in a photon-starved environment. Now, that would seem to be, in some sense, consistent with the fact that their emission lines are weaker as well.
Yes, yes.
But there's a very nice paper by Steffi Baum and a couple of others from 1995 that showed that the optical emission lines of FR1 radio galaxies are less luminous than those of FR2 radio galaxies due to a weaker ionizing continuum in the FR1 galaxies. So I think it's important to keep in mind that the weaker lines could be due either to fewer photons or to actually less gas, or, okay, I guess this would be consistent.
No, it's not. If they're saying less ionizing continuum, that
okay, so so what you're saying is actually that the origin of the weak lines would be the fewer photons rather than having necessarily much less gas, which would be consistent with what Baum et al.
Yes,
said.
I mean, this is not my idea. I mean, this is what Ghisellini.
I think it's an interesting question, whether if you do have weaker lines, is it due to less gas or fewer photons? And this is suggesting, again, fewer photons.
That's right. Continuum and line.
Unfortunately, we're at the end of the discussion.